All right, hi guys, welcome back. So it's Miss Smith again, and this is our final video for chapter 4. So here we're going to talk about resonance as well as formal charge. So these two things are going to help you kind of select the best Lewis dot structure, which was from our previous video. So watch that again if you don't quite remember it. But these two topics are going to help you pick the best Lewis dot structure for your molecule. So this video roughly corresponds to section 4.5 and section 4.7 in the third edition of your textbook. Here we have a Lewis dot structure, or two Lewis dot structures, for the molecule of ozone, which is O3. So let's look at our rules. We've already got them drawn for you, but you can always practice it on your own. So with O3, we have 18 electrons, so each of these have 18 electrons displayed here. We see that each oxygen has an octet. You know, we've got a double bond here between these guys. We've got two lone pairs. We've got the double bond and the single bond with one lone pair, and we've got a single bond and three lone pairs. So we see this orientation here. And then we see, okay, well, what if I had drawn this but kind of the mirror image? So instead of putting the double bond between the left oxygen and the middle oxygen, what if I put it between the middle oxygen and the right oxygen? We see that both of these structures, you know, everybody obeys the octet rule. You know, we didn't put any more electrons than we needed. You know, we have them all represented. So how do you decide which one of these is correct? So the answer is, in effect, both structures are correct. So this highlights a very important principle of the Lewis dot structure theory, and that is the existence of resonance. Resonance occurs when more than one valid electron dot structure can be written for a molecule. So it's important here to remember that the atoms have the same connectivity, so everybody has the same neighbor, but the electron positions are different. So usually you're moving around maybe some lone pairs and changing a double or a triple bond. So it's very important for you to recognize that these are not real structures. Ozone doesn't have two different structures, and the electrons live in a double bond, on one half of the molecule, in one structure, and then on the other half in the other. It's not true. It doesn't alternate between the two. The forms that you draw represent like the absolute extremes of the electron locations. So what the structure actually looks like is what we call a resonance hybrid, and it's kind of an average of all the resonance structures. So if we look back at our ozone example here, so we had our two different resonance structures. So again, our multiple bond, our double bond moved from here to here. So essentially the electrons traveled. We donated a lone pair to make the double bond between these guys, and then these guys just moved to kind of exist on this oxygen. So you'll see this double-headed arrow to indicate that two structures are, two resonance structures of the same molecule. But again, remember, we don't have this structure and then this structure of ozone. Remember, it's an average of these two structures. So what that means is that these bonds are kind of halfway between the length and the strength of a double bond and a single bond, an OO double and an OO single bond. So another way that we can write this is what's called the resonance hybrid, where you kind of just show the basic bonding, and then we have these little dots to indicate that, we've got a little bit of double bond character in both of these oxygen bonds. So the ability to kind of spread out these electrons is also called delocalization, and this gives the molecule kind of an inherent stability. So you can spread those electrons around and the molecule is more stable because of it. And remember, these are just kind of an oversimplification. When we draw them like this, simply drawing the Lewis dot structure with some little dots isn't a complete picture of the molecule, but for right now, it's a pretty good representation. Some of the key facts to keep in mind when you are drawing these resonance structures is, the first is that only electrons move. You're not changing the order of them. You're not changing how they're connected to one another. All you're doing is moving around lone pair electrons and multiple bonds. So everything has to stay at least bonded by one single bond. And then again, the total number of electrons never changes. You're not adding, you're not taking away any electrons. You're just moving them around. So here we've got SO2, has the same similar pattern as O3. So we take these electrons here. These guys can move to make a double bond. And these electrons that kind of make up the double bond can kind of hop over here and live on the right-hand oxygen. All right, so now we have the carbonate anion, so CO3 with a 2- charge. I want you to practice on your own and see how many resonance structures you can draw for the carbonate anion. So try that, hit pause, work on it, and then we'll talk through it together. All right, welcome back. So again, the first thing you want to do is draw just a Lewis dot structure, the best one you can for carbonate, and then we'll play around with the resonance. So the first thing you want to do is count up your electrons. All right, so hopefully this is review, but I'll go through it quickly. So we have carbon and oxygen in our structure. We have 1 carbon from the lack of a subscript. It brings 4 valence electrons to the party. So we have a total of 4 electrons from C. We have 3 oxygens, each bring 6 electrons, so multiply those two together, we get 18. Add those together, we get 22 electrons, but however, this is an anion. We have a -2 charge on our carbonate. So that means we add in 2 electrons, giving us a total of 24 electrons for this structure. Then we've got to pick our central atom, which again, just based on sheer numbers, also electronegativity, carbon's going to be in the middle, so arrange that first. Then you're going to surround it with the oxygens and connect them all with single bonds. So each bond represents 2 electrons. So now we're down to 18 electrons to place on our structure. So you fill the octets of the outside. So we're going to start with the oxygens. So this oxygen here has 2 electrons already around it. So we need to add 6 more to get it up to 8. All right, so we use 6 electrons to do that. So that leaves us with 12. So we're going to do it with the other 2 oxygens who are bonded the same. So they each need 6 as well. All right, so now we're down to 0 electrons. We've placed all 24. So let's go back and double check. All right. So we see that all the oxygens have their octets, so they're good to go. But let's look at carbon in the middle. We have 2, 4, 6 electrons around carbon. So carbon's pretty unhappy because he doesn't have his octet yet. So what we're going to do is share 1 pair of electrons from an oxygen to get us to have 8 electrons around carbon. All right, so I took my electrons from this left-hand oxygen, made it into a double bond. So oxygen still has 8 electrons around it, and now carbon still has 8. So to complete this Lewis structure, I'm going to put them in brackets and put my 2- charge. So there is my Lewis dot structure for carbonate. But maybe you're asking yourself, or maybe you took electrons from a different oxygen. So here's where we get the resonance structures. So instead of taking them from this left-hand oxygen, I could have taken them from the upper oxygen. So let's draw that structure. All right, so here's that structure. So essentially, I took my electrons from here, dumped them down to make a double bond with carbon, and then the electrons that were part of that second bond just went back to that oxygen. So here is my second structure. But again, I could have done it with the right-hand oxygen. So let's draw that structure now. So again, my electrons from the right-hand oxygen just came down, made a double bond between this C and this O, and then these electrons in the double bond went back up to reside on the oxygen. So again, you'll notice here I have 3 resonance structures for carbonate. So my answer is going to be C here. But again, just notice that my connectivity did not change. I have a C in the middle, surrounded by 3 oxygens. They all are hanging on by at least 1 single bond, and I didn't throw in any electrons, or any extra electrons. So just go through, make your best Lewis structures, and then see how you can change things up. So the next question regarding the same structures, the same carbonate molecule, asks what's the bond order for the CO bond? So I think we'll just talk this one through together. So remember, in regular structures, a single bond has a bond order of 1, a double bond has a bond order of 2, a triple bond has a bond order of 3. But here, remember, these structures are just kind of an average of all three of these structures. So we don't just have, this specific CO bond has a bond order of 2 and the other guys have a bond order of 1. They're all going to have the same bond order, and it's going to be some average of, all the bonds in the structure. So what we're going to do is count how many bonds are actually in between C and O in the structure. So we'll just look at this guy, for example. So here we have a double bond, so that's 2, plus 2 single bonds. That gives us 4 bonding pairs of electrons. And these 4 bonding electrons are spread evenly over 3 bonded pairs of atoms. So I have this CO bond, this CO bond, and this CO bond. So we take the number of bonding pairs of electrons, so 1, 2, 3, 4 bonding pairs, divided by the number of bonding pairs of atoms, so that's 1, 2, 3. So that's going to give us a bond order of 1.3. So what this means is that the bond length, as well as the bond strength, is going to be somewhere between the length and strength of a carbon-oxygen single bond and a carbon-oxygen double bond. So just for your own edification, this has been experimentally determined. So the length of a carbon-oxygen single bond is 143 picometers. The length of a carbon-oxygen double bond is 123 picometers. And the length of a CO bond in the carbonate anion is about 129 picometers. So we see it's in between these two values, and each of these CO bonds in this structure all have the same exact bond length. So we've talked about resonance structures, but one thing we talked about when we discussed Lewis structures is just because you draw it that way on paper doesn't mean that's the way that it actually exists. So what you'll learn to find is that not all resonance forms contribute 100% equally to the overall molecular structure. So essentially, just because you can move the electrons in one way doesn't mean that's the way they actually go. So we have to invoke and utilize something called formal charge that's going to help us kind of sort out which of these resonance structures is kind of the best of all the resonance structures. Formal charge is the charge an atom in a molecular ion would have if all the bonding electrons were shared equally between the bonded atoms. So it's really important to remember that these are just kind of a theoretical value. It's not an actual charge. Just because we say, oxygen has a -1 formal charge does not mean that it, holds an extra electron on it. We really just use formal charge as kind of an accounting system to kind of help us justify, one structure over another. And if you get into organic chemistry, it will really help you kind of tell where there's kind of a more negative site and where certain things are going to react. But that's a story for another day. So we can calculate formal charge by taking the number of valence electrons present in the atom. Again, this comes from the group in the periodic table. Then you subtract the number of lone pair electrons plus half of the number of bonding electrons. So really another way you can do it is to take the number of valence electrons minus how many lone pair electrons there are, so count them individually, minus the number of bonds. So here we're looking at the cyanate anion. All right, so you've already got a structure drawn and you're trying to justify it in terms of formal charge. So again, you're going to take the number of valence electrons minus the number of lone pair electrons minus the number of bonds, or half the number of the bonding electrons. So let's go through and calculate them one by one. So we're going to start with the oxygen. So oxygen is in group 6A in the periodic table. So it has 6 valence electrons. So 6 minus the total number of lone pair electrons drawn on the oxygen. So here we have 1, 2, 3, 4, 5, and 6. So we're going to subtract 6. And then minus the total number of bonds on the oxygen. So the only bond coming off of this oxygen is just this one bond here. So minus 1. Alternatively, you could say, well, I know in that bond we have 2 electrons, so half the bonding electrons would be 1. So same difference there. So we do this and we get a -1 formal charge on the oxygen. Moving on to the carbon. Carbon's in group 4A, so the number of valence electrons on carbon is 4. Minus the total number of lone pair electrons on carbon, we see none drawn, so that's -0. Minus the total number of bonds on the carbon. So here we have 1, 2, 3, 4. So -4, we get a formal charge of 0. And then finally, we're going to do the nitrogen. So nitrogen is in group 5A, so it has 5 valence electrons, minus the number of lone pair electrons, 1, 2, so -2, minus the number of bonds. So coming off the nitrogen, we have 1, 2, 3. And that's going to give me 0. So sometimes you'll see them written on the actual structure. So we'd say -1, 0, and 0 here. So again, calculating formal charge is really easy. Just if you can count total number of lone pairs, total number of bonds, and figure out how many valence electrons the atom has from the periodic table, you are good to go. There are a couple things to keep in mind when you're trying to use formal charge to justify your Lewis dot structure. The first is that you should always make sure that the sum of your formal charges adds up to the charge on the molecule. So this guy, if we took -1 plus 0 plus 0, that gives us a -1 charge, which tracks with the charge on the total ion. So if it's cation, they should add up to some kind of positive charge. If it's neutral, they should all add up to 0. The next thing is that your formal charges should be as close to 0 as humanly possible. So in this guy, they obviously can't all be 0 because we have a -1 charge. But usually the further away you get from 0, kind of the worse your structure is. And the third thing is that if you do have to have a negative charge, it should be placed on the most electronegative atom. And that's going to make your structure the happiest. So again, big points, the sum of all your formal charges in a molecule, so in a neutral molecule, must be 0. If you've got an ion, the sum of the formal charges should equal the charge of said ion. So when you move around electrons to make your different resonance structures, your atoms are going to have different formal charges each time. So here we've got a different arrangement of electrons, a different resonance structure of this cyanate ion. So it's your job now to figure out what the formal charge on each of the atoms are. So it goes from left to right. So the first number would be oxygen, then carbon, then nitrogen. So take a few seconds, figure that out, and then we'll work through it together. All right, so let's start on the oxygen. So oxygen again has 6 valence electrons from the periodic table. It has 1, 2, 3, 4 lone pair electrons in this structure, and it has 1, 2 bonds coming off of it in this structure. So the oxygen's formal charge is 0. If we go to the carbon, carbon again has 4 valence electrons on the periodic table. In this structure, it has 0 lone pair electrons, so we just subtract 0. And then it has 1, 2, 3, 4 bonds coming off of it. So that guy's 0 as well. Finally, we have our nitrogen. It has 5 valence electrons. It has 1, 2, 3, 4 lone pair electrons. And it has 1, 2 bonds coming off of him. So this nitrogen has a -1 formal charge. So our correct answer here is letter D. All right, one more time. We've got a different arrangement here, a different resonance structure. So figure this one out and pick your answer, and we'll go through it together. All right, so again, we'll go left to right, starting with the oxygen. So oxygen in this case still has 6 valence electrons. We have 2 lone pair electrons, and we have 1, 2, 3 bonds. So -3, -2, -3 gives us a +1 charge on the oxygen, +1 formal charge. For carbon, again, 4 valence electrons. We have no lone pairs, but we have 4 bonds still. So carbon continues to have a neutral or a 0 formal charge. And last but not least, the nitrogen, continuing to have 5 valence electrons. Here we have 1, 2, 3, 4, 5, 6 lone pair electrons and 1 bond. So -6, -1. That's going to give us a -2 formal charge on the nitrogen. So our correct answer here is going to be letter C. So again, as a reminder, not all the resonance forms contribute 100% equally to the overall molecular structure. The best case scenario is that you have all your formal charges as close to 0 as possible. If it's a neutral molecule, they should pretty much all be 0. And then the better structures have negative formal charges on the most electronegative atom, and then positive formal charges, if you have to have them, on the least electronegative atom. But again, closer to 0 is better. So, based on the formal charges that we just calculated for structures A, B, and C, which do you think is going to contribute the most to the resonance hybrid, and which do you think would contribute the least? So the first letter would be the one that would contribute the most. The second letter would be the one that would contribute the least. So look back at your notes, look at your formal charges, try to justify it, and then we'll talk through it together. Alrighty, so I have written the formal charges that we previously calculated up above. Again, if you needed to do the math again, that's fine, but I just kind of remembered or looked back. So remember, our rules are the closer to 0, the better, and the more electronegative atom gets the more negative formal charge. So looking at that first rule, closest to 0, the better, that's going to make choice C kind of be our worst structure. So here we've got 2 atoms being 0, 2 atoms being 0, and then we've got 2 as -1. So those aren't awful, but here we've got the oxygen, which is the most electronegative atom, carrying a +1 charge, and then we've got nitrogen over here at -2, so even further away from 0 than we were before. Now they still add up to the total charge of the ion, but this structure is just straight up terrible. So it is going to definitely contribute the least to our resonance hybrid. So we're between B and C here now in terms of correct answers, because C is definitely the worst. So looking at letter A, we have a negative charge on oxygen, and then B, we have a negative charge on nitrogen. So again, the more electronegative atom should carry the most negative formal charge. So here, oxygen is the more electronegative atom, so it's going to want to carry that -1 formal charge over nitrogen. So A is going to be your best structure. It's going to contribute the most to the resonance hybrid. And then C is going to be your worst. So our answer to this problem is letter C. We talked in the last video about the ability for some atoms, period 3 and below, to expand their octets. And you might have been wondering kind of why that happens. Well, here's kind of part of the reason. So here we have sulfuric acid, H2SO4. So if we make everybody have an octet, everybody's being happy. If we count our formal charges, the ones that aren't listed have 0 formal charges. Sulfur here has a +2, and 2 nitrogens have a -1. So this is an overall neutral molecule. All the formal charges add up to 0, but these aren't great. If you can avoid these guys having formal charges at all, it's going to be a better structure. So by expanding sulfur's octet and donating in 2 electrons to make a double bond here, and 2 electrons here making a double bond here, we see that we can have 0 formal charges for the entire molecule, every atom available. It also kind of shows you why you wouldn't donate a lone pair from the oxygens that already bonded to the hydrogens. You can look at the formal charges of what that would make, or why you wouldn't share 2 sets of lone pairs from the same oxygen. So you can draw those structures and kind of prove to yourself why those, in terms of formal charges, wouldn't be quite as good. So here we have 2 structures that represent the bonding for acetamide. So we've got carbons and hydrogens, nitrogens and oxygens. So we've got, the same bonding structure, but do you think that structure A would contribute more to the resonance hybrid, or structure B would contribute more? So which one's more accurate in terms of formal charges? Or do you think they would both contribute equally? So look at the formal charges, see what you can come up with, and we'll talk through it together. So the hint here was to focus on the oxygen and the nitrogen, which, if you pay attention, those are the only two that kind of change in terms of bonding. So this carbon with 3 hydrogens looks exactly the same. If we look at the carbon, it has a double bond and 2 single bonds, a double bond and 2 single bonds either way. So it's not going to change. Same with these hydrogens over here. So for structure A, let's look at our formal charges. We'll start with oxygen. So oxygen, again, has 6 valence electrons. It has 4 lone pair electrons and 2 bonds in the structure. So again, we have 1, 2, 3, 4 lone pair electrons, 1, 2 bonds. So that gives us a formal charge of 0 for that oxygen. For nitrogen, still 5 valence electrons. We have 2 lone pair electrons and 3 bonds, giving us a formal charge of 0. And again, if you can't quite see that, get the nitrogen. The 5 valence electrons comes from group 5A on the periodic table. 1, 2 lone pair electrons here. 1, 2, 3 bonds. All right, so these both have 0 formal charges. That's looking pretty darn good. But let's check letter B just in case. So letter B, the oxygen, we have again 6 valence electrons, minus 6 lone pair electrons, minus 1 bond, minus 1 formal charge. Nitrogen, 5 valence electrons, minus no lone pairs, minus 4 bonds, and we get a plus 1 formal charge. So hopefully it's very apparent to you. Since these are neutral molecules, they're both going to add up to 0. If you can go through and calculate the formal charges of each of the carbons and the hydrogens, convince yourself they're 0 as well. But between the oxygen and the nitrogen, both being 0 versus both being minus 1 and plus 1, which again is further away from 0, letter A is going to be your winner here. So this is your more accurate structure, and kind of the way that acetamide is actually going to bond. So formal charge is a really powerful tool to kind of help you justify different Lewis structures and kind of cast some aside, just based on bonding patterns. We spoke of common bonding patterns back in the Lewis dot structure video, but we'll remind you of them here. So again, just typically carbon likes to make 4 bonds. We see that in different places in these structures. So here we have 1, 2, 3, 4 single bonds around this carbon. This carbon has 1, 2 single bonds and a double bond, which again adds up to 4. So 1, 2, 3, 4. So it doesn't really care what the 4 bonds look like. As long as it's got 4 bonds around it, carbon's good to go. Oxygen likes to make 2 bonds and have 2 lone pairs. So we can see we can see oxygen make a double bond and have 2 lone pairs. If we have a structure like water, it has its 2 single bonds and it's 2 lone pairs. So again, it still follows that kind of standard bonding pattern here. Nitrogen likes to make 3 bonds, as we see here, and keep 1 lone pair to itself. Remember, that's all kind of derived from the Lewis dot structures of the atoms and the number of unpaired electrons that it desperately wants to pair up. So it's kind of a good starting point to kind of remember your common bonding patterns. So that about does it for chapter 4. Again, there's a lot of information, but it's going to be really powerful to kind of help you, think about these structures. So when you make bonds, you release energy. When you break bonds, you got to put some energy in. Not all bonding is created equal. Something that is ionic. We have pure charge separation, cations and anions, pluses and minuses, complete transfer of electrons. In terms of when you share electrons, they're not always shared perfectly. We've got polar covalent bonds versus non-polar covalent bonds. In the non-polar covalent bonds, we pretty much consider them to be sharing electrons completely equally. polar covalent not so much. And we use electronegativity to justify these. We can represent these structures in electron dot diagrams that we call Lewis diagrams, kind of honoring the chemist who kind of first put these forth. Again, we only focus on the valence electrons because those are the ones that are, used in bonding. So those are the only ones we really kind of care about with the chemistry in terms of it reaching out to other atoms. But again, there are some kind of drawbacks to these. The biggest thing is the concept of resonance. That, essentially just because you draw them in a certain way doesn't mean that's how they actually look, and electrons can kind of move around, and they're not completely static. So we use something called formal charge to kind of help us ferret through and figure out which are the better structures. So again, just work through problems, draw Lewis dot structures, and the more you do, the better you'll get. And as always, I'm here to answer any questions you may have. Thanks, guys.